There's a 21-to-1 gearing up for this speed, this flywheel right here. This is going 21 times faster than the unit. As you see, the pressure is still right about at the vapor pressure level, around 800 psi. The pump is the circulating pump right now is idle, waiting for liquid level to come up enough over a standpipe for it to pick up. If it doesn't pick up enough, one of our
the thrust we got. You see this little collar right over here on the shaft? Well, we had to go to that big old collar and make it steel hardened to 100,000 shear value, because we first started out with this collar. You see that big piece of steel there? That was the collar, and look what it did to it whenever we turned it on and we started applying that power to it. And by the way, these are pins. Those pins are steel hardened pins. It takes about 60,000 pounds of shear. And look what it did to them. Just snapped them right in half. So we knew we had some power when we turned it on, and the first thing that happened on the shaft was it just twisted the shaft and just tore that stuff to pieces. So we've got it real well fortified now. If all of us pulled against this wheel, we took about 30 people, we couldn't make this wheel turn. So when this comes down, though, it'll start turning, and you'll see the momentum that it builds up. Now, over here, we got the receiver, just like the receiver on the Joy. So once this CO2 comes out of the engine, liquid, it comes in and fills this up with liquid. You got a low side, and you got a high side. And you maintain that low and high side all the time. So it'll just sit here and run and run and run. So I guess with that explanation out of the way, I might as well just go ahead and let him turn it on. Rick, my assistant, why don't you just go ahead and turn it on. Now what he's going to do is he's going to go to the back and he's going to take the wheel off top dead center. When he gets the wheel off top dead center, the wheel will start turning. Now Charlie, you can just show us right here that the pistons, we got a double piston. One of these pistons go down while the other piston is coming up. So you see that one is rising while this one's going down. You hear this thing going? There's a lot of power there. Now when it hits the top, then it will get another hit, boom, and it'll go back down the other side. Now if you want, Ron, what we can do is we can just take a shot right down the middle here, and you can get those wheels. Now imagine a ton of weight spinning that fast with that kind of momentum. That's a lot of power. This wheel, you notice, is going very slow, about 10 RPM. That one in the back is taking off. Now, if you want to, Charlie, what you could do is just go back there and just get a closer look at the power on those flywheels. See the power on those flywheels? Now, let me tell you something. There's a lot of power being expressed right here. A lot of power. You hear the noise whenever those things are resonating. They sound like church bells. Okay, Ron, now, if you just take a look at the top here, right up on the top, we've got the high pressure, that's the pressure of the temperature of the CO2 in the building. And then the low pressure over here, that's the differential. So the difference between the high pressure and the low pressure is what's causing this thing to run. And it'll just sit here. Now, it doesn't go very fast, so let me tell you something about this. It's good that it doesn't go very fast because this would require no maintenance at all. This thing will last 100 years. That's how. This electricity right here, now you see it's upside down, but that's where it's at right there on the spinner. Okay, 7. So we got 7 amps, 110. Okay, Ricky, why don't you make sure your pump over there, right? Ricky's going to turn the pump on. We'll start pumping the CO2. Put it on there. Okay, can you see that one?
Yeah.
Got it?
8.9.
8.9. Okay, good enough, Rick. There it is. Going now. Making electricity. You will go up and down.
This is the Tesla turbine. This was developed by my hero, a man who I think is the greatest scientist that ever lived. We built it from his writings and designs. We talked to other researchers with the Tesla turbine in the process of building it, and they did have a lot to offer us, but we also discovered that there are a few unique things that evidently they're not thinking about. We did build it, and boy, I can tell you one thing. There's a tremendous amount of power in this device. It's unbelievable. This little bitty guy just took off, and as a matter of fact, it started going so fast and had so much power that at one point in time we just couldn't control it, and it came unloose from its moorings, and it almost did kill 2 of our researchers. But it's got a lot of power, I can tell you that for sure.
Generator of a special design. It's referred to as a transforming generator because it combines 2 separate technologies. Inherent in this structure are both a normal alternator and the makings of a transformer. And the reason why these 2 technologies are combined in this way is because this device is capable of doing something that a normal generating apparatus cannot do. Effectively, these windings can talk to each other. They communicate by a magnetic flux exchange. And in doing so, they change what is referred to in the electrical vernacular as the source impedance of the generator. Now, the reason for doing this is kind of interesting. Everybody's talking about how important it is to upgrade all of our technologies and save energy and what have you, and yet some of the most basic apparatuses that we use have never been revamped in the best way to achieve these ends. This particular device is intelligent in the sense that it monitors the amount of power that's required by the load without the aid of an electronic regulator, and in doing so it ensures the delivery of a constant power to the load at hand. Now, to demonstrate this and to demonstrate the fact that this generator is capable of tracking what we call dynamic impedance loads, what we're going to do is basically provide you with two different demos. The first one, we're going to energize a standard high-intensity floodlight, and you can note the voltage on the screen here if you can see it. And I'm going to bring it up to its normal brilliance at 120 volts, which will be generated within the generator. Then we're going to shut it down, and I'm going to replace this bulb with a mercury vapor lamp. Now, a mercury vapor lamp is customarily powered through a device known as a ballast. And the ballast tracks the changing impedance of the lamp and prevents the lamp from exploding by absorbing too much power. This generator, by virtue of its unique windings, can do the same thing and thereby eliminate the cost of a ballast. Just picture the effect of having an entire parking lot lit with mercury vapor lamps and having no ballast. For your information, the cost of a ballast is at least 50% of the entire fixture. So that'll give you an idea where we're going. Without further ado, let me get on with the demonstration.
Okay, so here we go. We're going to turn it on and light this one first. The interesting thing is this one doesn't run with any ballast, so we're proving here that we don't have any ballast. You're also going to see a sine wave that's pretty typical for this particular bulb, a sawtooth wave.
Yeah, the voltage on this generator will change as a function of the impedance. You can see the waveform here is pretty clear. Eric is turning up the intensity on the scope. It's primarily an altered sine wave that looks a lot like a sawtooth function. Anyway, the bulb is lit to its full brilliance. We have 120 volts RMS, and we're pulling a nominal amount of current. Just a second. Let me shut this down. Now, if we get this other lamp in here, what I'll do is I'll set the voltage to the same voltage as we had before, 120 volts, turn the machine on, and you can watch the intensity build. And if all goes well, this will start to assume the properties of a square wave, which is the machine's response to the dynamic impedance of the lamp.
By the way, you can't run this one without ballast. The other one you run with, and you prove that there is no ballast. And so this one right now, if it lights, that alone is a miracle. Oh, a miracle.
Now you notice that the waveform is bouncing around a little bit. That's because the plasma in the bulb is gaining strength. But eventually, when everything stabilizes, it will form a wave which is approximating a square wave. The reason that this is interesting is because a square wave has a higher order of harmonics in it than a normal sine wave, and therefore it represents a greater amount of energy being delivered to the lamp.
Go. So now what we're doing, he's taking his fingers. If you notice, it couldn't possibly be liquid nitrogen at 300 degrees below zero, or his fingers would be frozen. But he's levitating that, but you notice that it also wants to go to the left or the right because we have magnetic parts on both ends. A close-up also reveals to you that that is definitely not a spinning magnet. It's dead quiet, but his fingers are also showing you that it's not it's anything other than room temperature. So there you are, levitation at room temperature in a Meissner field.
Okay, basically this is a Yokogawa power analyzer. It's got a computer in it which is trying to figure out what it's doing right now. Okay, it's all done going through the auto diagnostics. The top display here is going to show you the line voltage that we're using. The middle display is trying to say power factor, and the bottom one has been set up to display watts. Now what we're going to do is really quite simple. There's two bulbs here, and there's a selector switch, and there's a variac. Variac takes power from the line, supplies it to this switch, and on one selection I can route the power directly to this first lamp, and on the other selection the power has to go through this oscillator circuit before it reaches the lamp. Now the meter is hooked up to the supply side of this, so it's going to see both effects, and it's going to register faithfully what's occurring. Now, let's first check it out by doing the positive power part of the demonstration, which is essentially the way your home works, the way most things work in the world right now. I'll bring this up, and as you can see, the bulb gets brighter. And I'm not going to go all the way up with the wattage because with the voltage, because this experimental circuit has low voltage transistors in it. I don't want to wreck anything, but I want the comparison to be fair. So we're doing about 96 volts here. Our power factor is about unity, 0.999 or 1 when it makes up its mind. And the wattage that we're looking at right now is 69.2 watts. And these are 100-watt bulbs, but without having the voltage up to 120, you're going to get a little less out of it. So that's all you got. It's a standard bulb. It's getting hot. It's getting luminous. All the things you'd expect. Now, we're going to turn this back down. Remember that number. It's 96 volts. I'm going to turn that down. I'm going to select the routing of power through the oscillator, and we're going to do the same thing again. So let me bring this back up. If you listen, you can hear the thing chirping away over here. There's about 96 point something. Okay, so we got the same voltage, 96, but look at this power factor, negative 0.032, and look at the wattage, negative 15.7. Now, that's a little bit peculiar.
Yeah, going back the other way.
You got it. That's the whole point. We're sending power back to the power company, and that's the significance of the negative number.
Yeah.
Now, the interesting thing about it is, see, power is like anything else. It can flow. It doesn't care which way it's going. All this hoopla about draining it only one way is so that they can also drain something out of your hip pocket.
What I'm going to do is I'm going to dial up some voltage here. Now I'll show you that there really is electricity here because you'll see the effect on the light bulb. See that? That's what Nikola Tesla is known for. The man that could have changed your whole entire world and you never would have paid for electricity in your lifetime, who could have given you free electricity 100 years ago, is known for this right here, little games that you sell in little novelty stores. That's pretty sad, folks. That is pretty sad. Now, right here I have a single wire, It's wired in right here. How many people know you can't send electricity over a single wire? You can't do it. Now the fact of the matter is, what we're going to do is we're going to use this wire as the ground. Why? Because they'd get mad at me if I drove a spike all the way through the floor of the foundation and tried to hit the ground out there on both of these sides of the stage. So since I can't stick these in the ground, I can't ground them. The only way I can ground them is with a single wire. So electricity is going to go through the air, and it's going to come back here, and what's going to happen is, by the way, if I just took this light and I would have touched anything that was grounded, the light bulb would light. Now, we're going to send the electricity all the way over here to this receiver. Over this cord. Move my thing over here just a little bit closer, Ricky. Let Ricky do it. Okay. I can fire Ricky. You I can just get mad at. No, I'll never fire you, Ricky.
Slaves have to be sold.
Slaves have to be sold. Than me. Probably everybody out there is a whole lot smarter than me, but I'm lovable anyway. Besides that, I own the company. You got to put up with me. Teddy bear. All right, now let's try it again. So you notice that it doesn't work if it's not grounded. So I've proven that point, right? Now we got it grounded. Look at that. Electricity's going from here over there. Now you notice that I'm standing here. I'm in terror. My hair is going up like crazy. Live electricity is coming across this stage. You see me interfering with it. That candle is flickering like crazy as I get over here. But you'll notice that if I get over here and I do it, it is flickering like crazy because it's regular electricity there where I'm interrupting those electromagnetic fields. But over here I'm not doing anything. I can dance or do what I want to do. I can dance like David danced. So you see, live electricity can indeed be shot through the air. It can happen absolutely harmlessly, doing no negative impact on the environment or on individuals whatsoever. And all we would have to have is little towers that are sending it through the air as far as anybody wants to send it. And it would be more efficient than any grid system or any wire that we got out there. All of that is because now what we're going to do is I'm going to take this ordinary light bulb and I'm going to prove to you that Tesla was right. So I'll just go ahead and prove it to you. Now this is a fluorescent bulb. How many people know you can't light a fluorescent bulb without ballast? Got to have ballast. Well, this one doesn't have any ballast. And also, this is a 12-volt battery, and you can't light a fluorescent bulb on a 12-volt battery, and especially without ballast. But I'm going to set this up over here so that my associate can do exactly that. And how many people know that in order to send electricity, you need to have a positive and a negative? Got to hook a positive to a negative. Well, we're going to show you that this is hooked up kind of unique because you're going to see you don't have to have a positive to a negative. And I'm going to just let my associate explain that to you.
Okay, we have a 12-volt battery here and a little box. Now this little box is not ballast, but it has an input side and an output side. Positive, negative on the input, positive, negative on the output. Now the input, we disconnect across the terminals of the battery. Negative, negative, positive, positive. On the light, we're going to take one of these terminals from one side of the light and hook it up to the positive here. The other terminal we're going to take back to the positive side of the battery. Hook up the power, lights the light. Now this is pretty strange because normally you'd have sparks flying and shorted out battery and all kinds of strange things going on. But just to show you that I haven't reversed the terminals inside of the box here, I'm going to switch this one here over to the negative side, and it doesn't light the light. So I haven't made any switches inside the box. Now, something even more amazing, if you take one of these off.
Now, you notice that when it takes one wire off, now we know we have to pass electricity through two wires, but evidently when you pass electricity through one wire, you only get half of it. See, because you notice that the bulb's only half lit here. So you only get half of it through one. No, you guys aren't buying that, are you? Okay? Well, you see, you can't pass electricity through a single wire, so what in the world is going on here? Well, what's actually going on is I'm completing the circuit right now, because you notice wherever I hold this, that's where the light goes. So it goes wherever I put my hands, and it's only going to be as lit as I allow it to be, because when it hits my hand, the circuit is completed through my body. That's because right now what is happening is, he's got a wire going up to his hand, you see that? And now the power is passing through his body, and then his body is sending the power through the air to my body, and my body is completing the circuit. Obviously, I really am completing the circuit here. Now, this is kind of interesting because right now what is happening is he's a Tesla coil, I'm a Tesla coil. Wouldn't you like to be a Tesla coil too? So power is passing right through the air. Now, we're going to show you something. We're going to show you that we are indeed doing this from the air, because the next thing I'm going to do is I'm going to put this speaker down, this microphone down, and then we're going to clasp hands. We're going to grab hands together. We'll show you the power of unity, solidarity, and brotherhood as we grab hands. We'll also show you we're completing the circuit directly, and watch what happens. Okay, so we are indeed completing the circuit. All right, now I'm going to do something else. What I'm going to do next is I'm going to take an ordinary bulb, just like that bulb, except this one is burnt out. You notice that? This is burnt out. This is a burnt out bulb. You can't light this bulb anymore. So not only is it pretty terrible, pretty amazing that you can light one of these without any ballast and with a 12-volt battery, but I'm going to go all the way over here across the room so somebody doesn't say, well, yeah, we're standing on top of one another for crying out loud, we're in an electrical field. I'm going to send electricity all the way over here to the whole other side of the stage, and I'm going to use a bulb that's burnt out to do this. So we're going to take a burnt out bulb. Now I'm going to take a single wire. So you notice here I've got a single wire going all the way back to him. The reason why I have one wire, you can't pass electricity over one wire, but I'm not grounded and he's not grounded, so we need a ground. So we have to have one wire to complete the circuit for the ground. By the way, Nikola Tesla did this 100 years ago when he was riding horses and buggies. Nikola Tesla 100 years ago sent electricity that he took from the ionosphere. He sent it across the countryside 26 miles away, where he had one of his little Tesla coils stuck in the ground. There were no wires at all because it was already grounded, because that was in the ground, the other one was in the ground. He's not grounded, I'm not grounded, so we're going to need this. But 26 miles he passed electricity. Guess how efficient it was? 100 years ago, it was 99.9% efficient. Hello. Now, right now today, I challenge any electric utilities executive, any engineer who works for the electric companies, if you can take electricity past 2,000 kilowatts of electricity, 26 miles, over any wire that you want, 99.9% efficient here, 100 years later, be as efficient as Tesla was 100 years ago, I'll give you $10,000 in cash. But my money's safe, because you can't do it. Now, so he actually was more efficient 100 years ago than they are today, passing power not through wires, through the air. Now let's see if we can complete this circuit here. Notice we're doing the same thing with a burnout bulb. So here we have a burnout bulb. We're lighting it again. He's passing the power from me. He's holding that in his hand. You notice that I'm completing the circuit again, just like before. Wherever I touch it, that's where it's going to end. Now, watch. I'll prove to you that he's sending the power to me for sure. It's going back over a single wire, but it's coming between his body and mine. He's going to take his thumb. Now, his thumb's on the end of the wire, so as he lifts it, he breaks the circuit. So, watch what happens when he puts his thumb up and down. See the bulb? He's breaking the circuit. He's sending the power to me. Now, he go ahead and stop. Now, I can order to start again. Now, it happens. Stop. Now, also, by
by the way, this is the way God makes halos. He uses all of our burnout fluorescent bulbs.